So it's a pleasure to introduce Timothy Buttsworth of the University of Queensland, who will speak on the prescribed Ricci curvature problem on manifolds with symmetries. And the meeting is being recorded. Oh, have you started recording yet? Okay. Okay, floor is yours.
All right. Thank you very much, Caroline, for the introduction, and thank you very much, everyone, for having me on this virtual seminar. Hopefully, we'll have had a lot of fun with this topic this morning. So, yes, the prescribed Ricci curvature problem. This is actually a decades-old topic now. Fundamentally, the problem is if you happen to have a smooth manifold M, and you're given some symmetric 0-2 tensor fields T on that manifold, can you actually produce a Riemannian metric G on that manifold whose Ricci curvature happens to coincide with T? So yes, as I said, this is a fairly old problem now. This, of course, is a partial differential equation. I'm sure everyone knows that the Ricci curvature, it's a second order, non-linear, and even non-elliptic differential operator on the space of Riemannian metrics. So this is a second order PDE, non-linear and non-elliptic, but nevertheless, it would make sense to ask about local results as well as global results. So in terms of local existence results, perhaps one of the most well-known and heavy-hitting results was produced by de Turck in 1981. If you're looking at a point P on the manifold, and it so happens that your tensor T is non-degenerate at that point, then you will in fact be able to solve this equation, at least in some neighborhood of that point P. Now, the proof of this result, well, it is a local existence result. Really what you'd want is just to appeal to ellipticity straight off the bat. Unfortunately, you can't quite do that, and that's precisely because of the diffeomorphism invariance of the Ricci curvature. Nevertheless, you can play games with the diffeomorphism invariance. In fact, perhaps a primitive version of the de Turck trick was used in this paper of de Turck's to actually solve this non-ellipticity issue. He later develops this idea into the well-known and celebrated de Turck trick that's now known and celebrated in use of the Ricci flow. Unfortunately, this original trick only works provided T was non-degenerate, and we can kind of see why we would expect that to hold, because as soon as the Ricci curvature has degeneracies, for example, let's say that it was 0, then somehow this problem, which most of the time is not diffeomorphism invariant, has become diffeomorphism invariant if T is equal to 0. So somehow that indicates to us that the techniques used to study this problem have to differ if T is degenerate. So that this is probably, yeah, as I said, this is probably the most well-known local existence result. But now, of course, it would be natural to go on to the problem of global existence. We encounter somewhat of a problem immediately because we observe that if you scale your Riemannian metric, the Ricci curvature is actually unchanged. So that means that if we're going to try and solve a problem like Ricci G equals T, the fact that constants are eaten up on the left-hand side somehow indicates that these constants need to reappear on the right-hand side. So perhaps a more reasonable problem to try and solve is, given a tensor T, can you scale it so that you can find a Riemannian metric G solving Ricci G equals CT? To produce some evidence that this may in fact be the correct equation to study, we have an interesting non-existence result that was given to us by de Turck and Carrizo in '84. Let's say that we're on a closed manifold, so compact, no boundary, and let's say that we're trying to prescribe positive Ricci curvature. Then it turns out that there is going to be some sort of cutoff constant C0 which depends on t, so that if you actually scale t past this cutoff constant, then there's no way you'll ever be able to solve this problem. So when we take this back to the question of can you actually find a constant c solving this problem, this theorem here sort of indicates that, well, there is an upper bound. There is an upper bound to what you would expect c would actually be. So this is a non-existence result. What do we have in the way of existence results? Not a huge amount, actually. There's this really classical result. This was a paper by Wallach and Warner in 1970, only 2 pages long, but it was a quite nice theorem. It wasn't presented exactly this way, but nevertheless, the implication of the theorem is this. Let's say you're on the 2-sphere. So if we think about easy situations in which we might try and solve this problem, well, in 1 dimension, of course, this is a stupid problem because there is never any curvature in 1 dimension. In terms of, well, the next highest dimension, 2D, maybe the 2-sphere is the obvious candidate on which to try and solve this problem. So let's say that we're trying to prescribe positive Ricci curvature again. When can we actually solve this equation? Well, the answer is you'll be able to do it if and only if the volume of this tensor t, which can be thought of as a Riemannian metric, if and only if the volume of that metric is 4 pi. In that case, the metric g you find which solves this problem is unique up to scaling. So in this setting, that means more generally, if you're trying to solve this particular problem for any positive t, you'll always be able to find a unique constant c so that this problem is solvable. The constant c needs to be chosen so that this new metric has volume 4 pi. So that's quite nice. And I think the proof is quite nice, so I might actually go through it. Note, this theorem was actually also proven by Hamilton in 1984, and it's sort of his notation that I'll be using to do this proof. So what makes 2 dimensions so special? Well, in 2 dimensions, the Ricci curvature is always in the same conformal class as the metric. We know that in 2 dimensions, the Ricci curvature is always given by the scalar curvature times g divided by 2, depending on your conventions. So this means that if we're going to insist that this Ricci curvature is the same as t, well, that means that g times some scalar function has to be the same as t. So that means that the metric solution g we find actually has to be in the same conformal class. So what that means is precisely this equation here. Given your tensor t, g has to be the same as t multiplied by some scaling function. Clearly that scaling function will need to be positive. So we may as well write that scaling function as the exponential of 2 times some smooth function, which we call f. The problem then becomes, well, t equals the Ricci curvature of e to the 2f times t. We can use our well-known formula for what happens when you take the Ricci curvature of a conformal metric. This is equal to the original Ricci curvature of t plus some terms. Those additional terms are quite simple if you're in 2 dimensions. And what you end up with is this equation here. Now, disclaimer that this is Hamilton's notation here. He took quite a few liberties with his definition of Laplacian and scalar curvature. His scalar curvature is perhaps off by a factor of 2 from what we'd usually expect. His definition of scalar curvature is so that on the standard round Einstein metric, his scalar curvature is 1, whereas usually, I think the usual convention is that that metric has scalar curvature equal to 2. And I also think that his Laplacian is different from what I think the Laplacian should be by a minor sign, but hopefully you can be convinced that this doesn't change the argument too much. Okay, what is so nice about this equation? So the Laplacian of the smooth function f, the Laplacian taken with respect to the metric t, that's supposed to coincide with the scalar curvature of t minus 1. This is a linear problem in f. It's just a Poisson equation. So that's quite nice. Using the well-known theory of Poisson equations on the two-sphere, we can see that, well, a solution is going to exist if and only if the average of the right-hand side is 0. So what we end up with is 0 equals this integral here. But what is so nice is, again, using this altered version of the scalar curvature, by the Gauss-Bonnet theorem, we know that this has to integrate to 4 pi. And of course, if we integrate 1 over the manifold, we get precisely the volume of the tensor T we were after. So a solution exists if and only if the volume is 4 pi. And in that case, it's quite easy, quite straightforward to demonstrate that the solution F of this linear equation is unique up to addition by a constant. But of course, addition by a constant is equivalent to scaling G. So this is quite nice. This is the entire problem, at least on the two-sphere. Okay, where can we go from here? Well, in terms of techniques that are available to us to solve this problem on higher dimensional manifolds, well, I guess the inverse function theorem is a natural place to look. So in terms of the inverse function theorem, can we actually solve this problem? I.e., if the tensor T we're trying to solve for, so remember we're trying to solve this equation here, if the tensor T happens to be close to some really well understood tensor, can we expect to solve this problem? And so this was work that de Turck did in 1985. Hamilton had a very similar result that seemed to have been done independently. De Turck's result, if your reference tensor is Einstein, so let's say you've got a smooth manifold alongside a smooth Einstein metric, G0. I didn't specify this in the theorem, that was unfortunate. So M is going to be closed, and the Ricci curvature of this Einstein metric is going to be something positive. So if you happen to be in this situation and you have a look at the kernel of the Lichtner-Roentz Laplacian associated to this Einstein metric here, if that happens to be one-dimensional, then yes, you can actually solve this problem whenever this tensor T is close to G0. So how does the proof of this theorem go down? Well, what does the Lichtner-Roentz Laplacian have anything to do with this? When you use the inverse function theorem, of course, you have to linearize your operator. When you linearize the Ricci curvature, the Lichtner-Roentz Laplacian pops out. It's one of the key terms. Now, what's going on here? We've got the Lichtner-Roentz Laplacian here, but what's all of this stuff over here? Well, G is the gravitation tensor. You may be familiar with this tensor. You take the tensor itself and subtract a half of the trace of that tensor with respect to your metric. Delta is the divergence. And delta star is the formal L2 adjoint of the divergence. It can also be interpreted as the symmetrized covariant derivative. Now, if we're looking to apply the inverse function theorem, it would be really, really nice if this term wasn't here. This is a Laplacian. Everything works out nice. If this happened to be all the linearization was, we'd get the result almost immediately. Unfortunately, we do get this extra term here. This is somehow a symptom of the problems caused by the diffeomorphism invariance of the Ricci curvature. So the proof of existence somehow has to deal with this extra problem term there. All right. Our proof somehow needs to respect both of these terms here. So in terms of the proof, it turns out to be quite nice to take this decomposition here. we express our space of symmetric 0-2 tensor fields as a direct sum. We express it as those tensor fields which are divergence free, alongside those tensor fields which are in the image of the symmetrized covariant derivative when it acts on one forms. Now, why is this decomposition so useful? Well, if we happen to be at an Einstein manifold, then the Lichtner-Rowitz Laplacian actually preserves this decomposition. This is just a computation involving lots of commuting of derivatives. So yes, because our reference metric is Einstein, it turns out that the Lichtner-Rowitz Laplacian respects this decomposition. Okay, that's great. So because this operator is nice and elliptic, what you can show is that if you look at the Ricci curvature map applied to not the whole space of symmetric 0-2 tensor fields, but if you just apply it to metrics which look like this, so your reference metric plus anything that's divergence free, then that is going to be a Banach submanifold with appropriate notions of what Banach spaces we're dealing with here. It's a Banach submanifold, and its tangent space happens to be complementary to the image of delta star. Now, why is that so useful to note? Because delta star, that's precisely the tangent space of the action of the diffeomorphism group. So the idea is that if you pick any tensor T that's close to G0, because you can interpret delta star as the tangent space of the action of the diffeomorphisms, you should be able to find a diffeomorphism so that when you pull back T by that diffeomorphism, it actually lands in this Banach submanifold here. So this is more or less the proof. Of course, there are lots of technicalities that I didn't get into, like what's the Banach space, but this is more or less the idea of the proof. Okay, so I think that these are most of the heavy-hitting classical results that I'm aware of. Now, there are a few others, of course. Now I want to go into what happens with the imposition of symmetries. Okay, so if we're going to impose homogeneous symmetries, where should we start? Well, we know what the problem is on the 2-sphere, so maybe it makes sense to look at the 3-sphere next. What sort of homogeneous symmetries can we look at? Well, the 3-sphere, we can think of that as a homogeneous space being acted on transitively by SO4. It turns out that that's the sort of useless homogeneous symmetry to look at in the context of the prescribed Ricci curvature problem, and that's because in that context there is only one G invariant metric up to scaling. Certainly a much more interesting symmetry to impose on the 3-sphere is SU2. So we've got the 3-sphere, we pick a positive T on the 3-sphere, we try and solve this Ricci curvature up to scaling that we were just looking at, and we want to insist that T is invariant under the transitive action of SU2. In this case, the problem is solvable. No matter what positive SU2 invariant T you find, you'll always be able to find an SU2 invariant metric G, which solves this problem. The constant C that you choose is uniquely determined, and G, of course, is again going to be unique up to scaling. Now, a couple of words on the proof of this result. The Lie algebra of SU2 admits the well-known Milnor frames. So the proof of this result is that, well, if you pick any Riemannian metric G, you'll always be able to diagonalize it in a Milnor frame. And so the idea then is just to solve the polynomial equations you end up with when you look at this problem in a Milnor frame. There is a subtlety here, however, and this is the issue of uniqueness. Usually the proof goes pick T, diagonalize T in a Milnor frame, and then you get your existence by find a G which is diagonal in that same Milnor frame. So there is a subtlety here that I don't think even Hamilton dealt with, and that's the issue of what happens if T is diagonal in more than one Milnor frame. You pick a new Milnor frame. Does the G you find in that new Milnor frame, is that going to be the same as the metric G that you just found? It turns out that in this case, the answer is yes. The answer you get is independent of the Milnor frame that you choose, but that requires a bit of additional work. This additional work is something that I did a while ago now. I was looking at this problem, this issue of uniqueness for the SU2 invariant tensors on the three-sphere. But of course, Milnor frames are not unique to the three-sphere. Any three-dimensional unimodular Lie group will admit such a frame. And something that I did was classify the existence and uniqueness of solutions to this problem on any three-dimensional unimodular Lie group. Okay, so that's more or less the story in 3 dimensions as of yet. What can you do in general? Like the Einstein equation, the prescribed Ricci curvature equation has a variational interpretation, and so that's very, very useful. So to describe this result, let's suppose that you do have a compact homogeneous space. Let's say that you're trying to prescribe positive and invariant Ricci curvature again. In this case, if you're trying to find a solution to this problem, by which I mean trying to find a G invariant Riemannian metric G whose Ricci curvature is the same as T, at least up to scaling, those solutions are exactly the critical points of this functional here. So the functional is take a metric and find its scalar curvature. Now, in general, this is not going to be a functional. This is just going to be another function on the manifold. But of course, in the invariant setting, scalar curvature is constant. So it makes sense to interpret this as a functional. Now, you may be quite aware that for the Einstein metrics, the Einstein metrics are critical points of the total scalar curvature functional, subject to the constraint that the volume of these metrics ought to be 1. So of course, if we're trying to use the scalar curvature functional to solve the prescribed Ricci curvature problem, our constraint somehow has to involve the tensor T, and that's exactly what this is. We restrict attention to those G invariant Riemannian metrics G, such that the trace of the tensor T that we're trying to prescribe, the trace with respect to that metric, is exactly equal to 1. So Pouliamotov has produced many existence results with several collaborators on solutions to the prescribed Ricci curvature problem, precisely using this variational approach. So this involves a lot of, one needs to understand very, very clearly the asymptotic behavior of the scalar curvature functional on this submanifold at infinity. So there are several results on the prescribed Ricci curvature problem in the homogeneous setting, but what I want to spend a lot more time on now is the cohomogeneity-one setting. So in full generality, it seems like the partial differential equations that you get by looking at the prescribed Ricci curvature problem, they are pretty difficult, and so making homogeneous assumptions is quite natural. What I like to focus on is the cohomogeneity-one symmetries, because you can have a lot of, in my experience, you can have a lot of interesting behaviors that you wouldn't otherwise get in the homogeneous setting, and that you wouldn't really be able to study properly if you were looking at the PDE in full generality. I find this to be a rather nice intermediate step here. Okay, so where do we begin? What's the most natural cohomogeneity-one manifolds to study this problem on? Well, we can go back to our good old three-sphere again. Let's say that we're trying to prescribe a positive Ricci curvature on the three-sphere. Let's say this time that T is O3 times Z2 invariant. So let me try and draw a picture here. if we think of our three-sphere here, and we think of all of these orbits as two spheres, let's say that this is the equator here, then this O3, this is the rotational symmetry. So this is invariance under these kinds of rotational symmetries. Although it's not strictly necessary, it is quite convenient to also impose that the tensor T we're looking at is Z2 invariant. So that means if you, it's symmetric across the equator. So these are the types of tensors T we're looking at. Now, what is quite interesting is that Hamilton needs to impose an additional assumption on T here, one that doesn't really have a good analog in the homogeneous setting. We need to insist that T, which is positive and therefore has its own Ricci curvature, it turns out it's useful to impose that this metric T has positive Ricci curvature itself. This is an interesting condition because, well, as I said, there is no obvious analog of this in the homogeneous setting. Once you have such a tensor T, you will in fact be able to solve the prescribed Ricci curvature problem. The solution you find is again going to be O3 times Z2 invariant. Now, I think the proof of this result is quite interesting, and I think it's something that I would like to go through. Now, in the cohomogeneity-one setting, it's probably well known that the equations that we end up with are going to be ordinary differential equations, depending on a single parameter. That parameter I'm going to think of as being R. R is going to describe how far through the manifold we are. I'm going to call this point an R equals -1. I'm going to call this point R equals 1. And the equator is going to be R equals 0. So it might be worthwhile trying to have this picture in the back of your head as we go through this. Okay, this is a bit heavy perhaps. These are the equations. So what's going on here? Well, to describe all the functions here, I'm going to start off by introducing Q, which is the standard metric on the two-sphere. Then the metric G, which I'm trying to find, it looks like this. It looks like h squared dr O times dr plus f1 squared times q restricted to the two-sphere. So in terms of this picture we had before, this f function is describing how big any one of these S2 fibers are. So clearly at r equals 1 and r equals -1, f1 needs to vanish. H squared is sort of describing how quickly we're traveling through this manifold here. So that's G. So the point is, for these equations, we're trying to find positive functions f and h. Now, what does the tensor T look like? Well, the tensor T is going to look like this, going to have a very similar form to the metric, because again, we know that T has to be a metric. T1, and then again multiplied by the standard metric on the two-sphere. Now you might be wondering, well, there are two functions for the metric here. Shouldn't there be another function for T right about here? Now, this is where we play with the diffeomorphism invariance of the Ricci curvature. We can always reparameterize the three-sphere so that the coefficient of this term here is just equal to 1. Unlike for the Einstein equations, we can't do this simultaneously with the metric G. So that's why we need to insist on having a function h squared up the front here. And also I've changed my C1 has become a C. So these are the prescribed Ricci curvature equations here. We're basically we're given a positive function T, and we're trying to find positive functions f and h, solving this equation here. Now, what's all this down here? Well, again, if we think about r equals 0 being the equator and r equals plus or minus 1 being the endpoints, since we're insisting on Z2 symmetry, that means it would suffice to actually study the problem on half the manifold. So that means we would get boundary conditions at both r equals 1 and r equals minus 1. This top line here, these are the first order smoothness conditions required to insist that the metric closes up smoothly at the r equals 1 singular orbit. This second line, these are the conditions that we need to impose to insist that our metric has Z2 symmetry and does so smoothly. So of course we need at least the first derivatives of both f and h to be 0 in the middle. So yes, this is the boundary value problem we have to study in order to solve this problem. It looks a bit hairy. Hamilton's proof, Hamilton in his 1984 paper, he had a lot of very funky tricks to solve problems like this. This one, it turns out that a convenient trick to use is to simply introduce the function L, which is given by minus f1 prime divided by h. Turns out that once you make this substitution and see what the equations tell you in terms of this function L, they tell you this. They give you a single first order equation for L. So this is quite nice. L prime squared happens to be the same as C1 divided by 2 times C1 times T1 plus L squared minus 1. The boundary conditions have become something quite nice as well. We need to insist that at the equator, L is 0, and at the very, very end, L1 is the same as 1. Okay, so how do we solve this problem? Presumably this is much easier to solve than the full equations we saw on the previous slide. So how does one go about solving this? Well, the way to do this is to sort of ignore this condition for the moment and just think about this initial value problem. You've got a first order ordinary differential equation. You're starting at L0 equals 0. In order to make this look more like a first order ordinary differential equation that we're used to, we'd have to go L prime is equal to the square root of some stuff. What's important to note is that the absolute value of the right-hand side is actually controlled by C1. Let's say it's controlled in terms of some constant times C1 times the absolute value of L. So the right-hand side has at most linear growth. And so that means we're always going to be guaranteed a solution to this problem, provided C1 is large enough. Because of this bound on the growth, the only issue we need to worry about is what happens when what's inside the square root gets close to 0, because then the problem fails to be Lipschitz continuous and therefore amenable to use of the standard existence and uniqueness results for solutions of the IVP. Making C1 large avoids this problem because, well, by forcing C1 to be large, we can see that, well, L is going to be growing quite quickly, and so we stay well away from places where this term here might in fact be 0. Okay, so we've solved the initial value problem for certain large values of C1. The proof then becomes completed by saying, let's just lower C1 until we don't get solutions anymore. What's going to happen at that final solution? Well, at that final solution, again, because the only problems caused by this problem, the only problems that arise are when what's inside the square root happens to be 0. As you lower C1 to this final solution, you're going to end up with a solution to this equation such that this term here actually equals 0 at some point. By insisting that the metric t has positive Ricci curvature, what we're insisting is that the second derivative of t1 is actually less than 0. Actually, no, we're insisting that the square root of t1 is less than 0. And by making this assumption, it turns out that you can't have any degeneracy. At the very, very last solution, you're not going to have any degeneracies except at the very, very final time. The degeneracy occurs where what's inside the square root is 0, that only occurs at t equals 1. But this is actually what we're after, because if this function here is 0 when t equals 1, at t equals 1 we know the metric tensor, that the Ricci tensor has to disappear. So we end up with this condition that we wanted in the first place. So this is all a bit technical, but the idea is that you raise C1 and then lower it until you get a solution. Now, in terms of my own thinking behind this problem, this I actually found to be the most conceptual challenge to this problem. The reason for that is that, well, my intuition was thinking along the lines of the Einstein equation. If you're solving Ricci G equals CT, and you're making C large, my thinking was that, well, in the Einstein equation, in the setting of the Einstein equation, when you make C large, you sort of make the problem more difficult to solve, because you have to be shrinking the manifold if you're insisting on the Ricci curvature being large. But somehow in the prescribed Ricci curvature equation case, this is doing the exact opposite. C is somehow regularizing solutions to this problem more than we need, and so we need to lower C1 in order to get the critical value of C that we want. So I don't really have a good explanation for that, but certainly it's interesting. All right, now moving on to some more recent work. Recently, I've been looking at the problem, the prescribed Ricci curvature equation on products of spheres. So the problem now is, well, we're trying to solve Ricci G equals CT, except now the manifold we're dealing with is the product of two spheres. The first of these spheres is D1 plus 1. I need to insist that both of these DI numbers are greater than or equal to 2. The second sphere is the sphere of dimension D2. And this time I'm going to be looking at metrics which are OD1 plus 1 times Z2 invariance, like what we saw with the 3-sphere previously, but we're also going to insist on O of D2 plus 1 invariance on the D2 factor as well. So this again is a cohomogeneity-one action. Last time the singular orbits were just single points, 2 of them in fact. This time the singular orbits are the north and south pole producted with this sphere of dimension D2. Okay, what does the prescribed Ricci curvature problem look like this time? Well, maybe it would be best to describe what the functions are. So if Q1, let's say that Qi is the standard metric on the sphere of dimension Di, then this time the metric that I'm looking for is going to be h squared dr O times dr plus f1 squared times the standard metric on the sphere of dimension D1 plus f2 squared times the standard metric, Qi there, Q1, Q2, restricted to the sphere of dimension D2. So the problem is I'm trying to find positive functions f1, f2, and h, solving this particular problem here. Like before, T1 and T2 are going to be the components of the Ricci curvature tensor. Now we have basically the exact same smoothness conditions as before, But since we're talking about an additional function, that means, of course, that we need additional smoothness conditions. So we need to insist that at both the singular orbit and at the equator, the first derivative of this f2 function vanishes. And we also need to insist that at both the middle and at the end, f2 is strictly positive. Now the question is, how does this relate? How does this relate to what we just saw for the three-sphere? Well, in a very naive way, one can actually see that the equations we get here do in fact become identical to the equations we just saw if f2 is constant. If f2 is constant, then the metrics that I just described actually produce a direct product structure. In general, if f2 is non-constant, then the metric on this product of spheres is just a warped product. But if f2 is constant, this just becomes a standard direct product metric. This equation basically becomes negligible. And these equations here are precisely the equations we already saw for Hamilton's theorem. Now, what happens in general? So if f2 is constant, I said that these equations are the same as Hamilton's. What happens if f2 is constant, however? What happens if t2 is constant? Well, this is actually quite interesting because if we have a look at this equation here, this equation satisfies a maximum principle for the function f2. We've got this nice diffusion term here, and every other term, these three terms all have f2 prime attached to them. So they're all transport terms. The only terms that don't behave like this are these terms over here. 1 minus c2 t2 on f2 squared. Now, if we suppose that t2 is constant, then 1 minus c2 times t2 is constant. And that means that this term is always going to be positive on the whole thing, it's going to be negative on the whole thing, or it's going to be 0 on the whole thing. Now we're trying to solve this equation subject to Neumann boundary conditions. And so from the maximum principle, what we can see is that the only way we can solve this problem is by insisting that this term must be equal to 0 in the case that t2 is constant. So this is why you may have noticed earlier on that in general, I've actually included two scaling constants this time. C1 for the sphere of dimension d1 plus 1, and C2 for the sphere of dimension C2. So this is quite natural, and this is the reason. It's because of the product nature of the problem. In general, if let's say that your manifold, your tensor T is de Rham irreducible, then it might be natural to insist that only one scaling constant is needed. But for these direct product manifolds, it seems that two scaling constants are necessary. So the prescribed Ricci curvature problem that we're trying to solve is this equation here, subject to the boundary value condition, the boundary values that we'd already seen, plus these two extra conditions here. Okay, can we solve this problem? Well, this is work I recently completed with Anusha Krishnan. It turns out that yes, but like with Hamilton's result, we need to impose additional assumptions. It turns out that the natural conditions that are needed to generalize Hamilton's insistence that the metric T has positive Ricci curvature are these conditions here. These are actually, in the case that T2 is constant, these conditions are a bit weaker than Hamilton's, but they do the same job. So if we insist that T1 and T2 have this monotonicity property, and we also insist that the curvature of the sectional curvature associated to T1 is strictly negative at the equator, then you would in fact be able to produce a solution with the same symmetries as the original tensor T. Now, the proof of this result, it's much more complicated than Hamilton's original theorem. The reason for that, of course, is that the equations are much more complicated. Hamilton managed to produce
Tim, I can't hear you. Is it just me?
Yeah, I can't hear either. You seem to have lost your audio.
Yes. What do we do? I'll try to call him.
Yeah, I think he lost hours because he's still talking.
It is.
Hi, Tim. We can't hear you for the last 10 or 20 seconds. Can you hear us?
yes, I can hear you. I think
All
my
right.
iPad logged. Fortunately, my phone's still here, but I think my iPad logged me out of the Zoom meeting.
Oh, I see. Yeah, it froze. It appears to be frozen.
Yes.
Can you disconnect and reshare again?
Yeah, I'm just trying to log back in now.
All right.
Actually, while that's happening, I'll make an announcement. We're going to be taking a holiday break, so we won't resume until January 13th. And you'll now find the schedule in your own time zone if you go to the website and look at scheduled talks.
Timothy, we cannot hear you.
I might just have to get the audio from the phone then.
Oh, we can hear you.
I think you can see my screen.
Okay, but mute your second device.
Oh, I'm almost finished.
I understand, but we hear you twice because
I just muted the tablet, so maybe now can you try again, Tim?
Yeah, are you hearing this now?
Yeah, now it's coming out great.
Perfect.
Okay. So the idea is that so the idea is you try and solve this problem for C1 particularly large.
We need the phone close.
C2. Sorry, what was that?
I think the phone
yes.
is closer because that's your mic. Yeah. All right.
Ramiro, ¿y si
Okay, is
con
that
los auriculares con el teléfono?
Yeah,
I think it works. I think it works great now, right?
Okay, good. So C1 is chosen to be especially large so that solutions can be found, at least so that C2 can be varied so that the smoothness condition for F2 can be satisfied. And then the idea is similarly to what we saw earlier, one continuously lowers C1 all the while changing C2 until at some point you can't do this anymore. We need to show that this last solution that we ended up with is in fact the solution that we're after. And this can again be demonstrated by using these sectional curvature conditions that we'd already imposed on the metric T. So the style of the proof is quite similar, massively complicated by the fact that the equations are much more challenging, but in the end we're able to get the existence result we're after. So I think I'll leave it there. Thanks for your attention.
Thank you for a beautiful talk. Are there questions? Oh, yeah. Are there questions?
Can I ask a question? So, Timothy, in this theorem, I don't quite understand where are the singular orbits in this notation. So this is acquired at 0 and 1, and where are the singular orbits?
T equals 0 is the equator. 0 in this notation, 0 is the center of the manifold. So this is the equator of the sphere of dimension d1 plus 1 times.
And one is a singular
sphere
orbit.
dimension d2.
One is a singular orbit.
Yeah, T equals plus or minus 1 of the singular orbits.
Okay.
So this is why we need to insist on all of the evenness conditions at T equals 0.
And why is the metric smooth? There are no further condition at the end, at the singular orbit?
That's an excellent question. So generally, there are many smoothness conditions you need to verify. The ones that I listed here were I think they only give you continuity, in fact. There are a few more conditions that you can check to make sure that you have C2. But once you have C2, you're good to go. And that's because of a classical regularity result by de Turck and Kasdan, which says that if you've got a C2 metric whose Ricci curvature is non-degenerate, then the metric will always be at least as smooth as its Ricci curvature. So if we insist that the tensor T is smooth, then finding a C2 solution is enough, because it will then automatically be smooth as well.
I see. So there are further conditions on T, but just because they're smooth. I get it. Okay. Okay.
Are there other questions?
Tim, can you say something about uniqueness for the solution?
So uniqueness, yes. So Hamilton's original theorem, he also got uniqueness as well. So Hamilton gets uniqueness as well. The way he does that is simply by, well, as soon as you get to a single first order ODE, verifying uniqueness is actually quite straightforward. For us, the only situation, we weren't able to produce uniqueness. The main reason for that is that the main tool we used was topological degree theory, which is really great for getting existence proofs, not so great for uniqueness. However, in the special case that I described, that T2 is constant, if T2 is constant, then as we saw, C2 is determined uniquely. And F2 is constant. So from these equations, if T2 happens to be constant, then C2 is determined, F2 is constant. Once that happens, you can just ignore that equation and you're left with the same equation that Hamilton had. And so then uniqueness would then follow. So in general, we don't really know. I would expect the solutions to be unique, but the only situation in which we know that for a fact are in pretty simple situations.
Great, thanks.
And so when I say uniqueness, what I mean in this context, the metric solution is unique up to 2 scaling factors. If you scale the metric on, if you've got a direct product manifold, you can scale your manifold individually on those 2 factors and get the same Ricci curvature. So in that setting, there's a 2-family parameter of solutions, which is why you would expect to need two scaling constants in the first place.
Are there any other questions?
I have a quick question too. So you mentioned a variational characterization in the homogeneous case. Is there any variational characterization here in the cohomogeneity-one case? Can you write the system as the Euler-Lagrange equations of something?
More in general, in Hamilton's 1984 paper, he did actually write a variational interpretation, but it's not one that I've ever really seen used with any success. It's something like Ricci G equals T. So this is one problem with it. It talks about solutions of the problem without the scaling constant. So Ricci G equals T if and only if it's a critical point of, I think you take I think it's that. You got to try and find a critical point of this particular problem here. But yeah, as I said, I've never seen that actually used to, I mean, you can think of, you might think that this is quite similar to what happens in the homogeneous case. But in the homogeneous case, the key observation that was needed was that somehow this is the wrong equation to solve. And so what the correct interpretation is in full generality, I'm not sure.
Can't you just do the same thing as an homogeneous case? Look at the total scalar curvature and under the constraint that the trace of T is 1, and then the critical points for Ricci equal to C times T for some C.
Yeah, so if you want to build that T in there, you can probably do it with a constraint. Yeah, that's kind of, yeah.
It holds in general on a compact manifold.
Yeah. Yeah, I guess my...
But the function is not as nicely behaved as it is in a homogeneous case. So it's hard to use that. Just like in the Einstein case, it's hard to use that to produce solutions.
Yes, I can imagine that even verifying the, well, I think even in the homogeneous case, even in the homogeneous case, in full generality, you don't expect this functional to satisfy the Palais-Mal compactness condition. And so...
No, you don't. You don't.
Yes, I think going even the homogeneous case, you kind of stuck with not using the mountain pass theorem, and so you kind of have to go for global maximums.
Okay, makes sense. Thanks.
Are there any other questions? If not, thank you again for a really nice talk.
Thank you.
Thanks, everyone.
Thanks. And then we resume on January 13th after the new year.